Okay, we're continuing here with quadratics, which I think for now is our last section on this, I believe. So we've talked about how if you can get a quadratic in standard form, that vertex, which is really just the shifts, it's you moved it right, you moved it up and down. That's the same exact thing we were doing when we did transformations. And in our last section, we looked at how valuable it can be to use the vertex for word problems. Because if your quadratic's upside down, then that vertex is the maximum. Now, let's do a little prep work. We got a few more of those examples. This is actually the section I did not remember. This is the section that has the more typical problems that you'll find. So let's get through this and we'll get to the word problems. Okay, now we want to find the x-intercepts. All right, well, that's when this equals 0. All right, so if I wanted to try to factor this, what we'd find is that there is no easy factoring. So the way to go with this would be, they're going to go kind of a convoluted route here. You could put this in standard form and then solve it using the square root property, which means just work it around to the square root. I'll show you in a second, but the easier way to do it would just be the quadratic equation. So since it can't be factored, I've got negative b plus or minus the square root of b squared minus 4ac all over 2a, and the a is another 2. Now if I crunch this down, I'm going to get the intercepts. That's what the quadratic is doing. Now I'm going to take you through, because I don't want to crunch all that math. I'm going to show you what they did. They did like something we were doing before. They found h and k. Quadratic would be so much easier, but they found h, plugged that back in, and now they had k. Okay, so then the a was from the original. That's a. So now we've created this standard form of the quadratic. Now look what they do here. It's clever. We can solve a quadratic like this. Setting equals 0, send the 6 over, divide both sides by 3. Now at this point, take the square root of both sides, and that's how they got to this line there. And then if you send the 1 over to the other side, it becomes negative 1, and there are my two solutions. Those are the x-intercepts, the roots, the zeros. They're all synonyms. So we would have got there just as easily by just going through this, but it should turn out to be the same as they got. Okay, so same thing here. I'm going to put it in the general form. It's not in the proper order. So we would do this. Now you could do like they did. We're trying to set this equal to 0. We want to find the x-intercepts. Well, I don't think we talked about the y-intercept. The y-intercept of this function would be when you're putting 0 in. So you'd have 0 squared minus 6 times 0 plus 13. Well, y would then be 13. So the y-intercept would be 0, 13. That one's easy. Now we want to find where this equals 0 in order to find the x-intercepts, which tends to be the more important kind of problem. Now, this is not going to factor again, so I would do negative b plus or minus the square root of b squared minus 4. So b squared is negative 6 squared minus 4ac, all of that being divided by 2 times a, which is just 2. I'm going to have 6. Yeah, now I see where they're going with this. So if you had tried this on your own, you're going to run into some trouble here. This is going to get you negative 16 over 2. So we haven't talked about complex numbers, I don't believe, at this point. So what you would get here is 6 plus or minus 4i. So it's gonna, you can't have a negative under there, but this is the complex number. Again, I don't know if we've done this. So This would have been a hard one to do on your own. But so this is the complex number. This can be handled using complex numbers. But what their point is, when they're asking if there are any, there aren't. A complex number is not going to show up as an intercept on the graph. So we found this as an answer. Theoretically, these are intercepts, but because they are imaginary, involve that I, then they are not actually going to hit the line. So this must be some graph that doesn't ever touch the line. All right, now this is what I was alluding to. I was surprised it wasn't in the last section. I guess I divided it in such a way to keep these as their own kind of problem. But so we know, if you look at this equation, that I've got a parabola that's upside down. So the vertex is going to be the maximum. So here's where we'll see it in physics and stuff all the time. They're giving us an equation of something being thrown off a building or shot off a plane or whatever, tossed off a mountain. And this formula tells me the height at different times. Well, when does the ball reach the maximum height? That is the h of the vertex. You see, if this is it, this is a function where it's about time and height. So it's not x's this time, it's time down there. So if I find this, the t, I've got the time. If I find the k, I have the height. So when does the ball reach the maximum height? That's just finding h. 2.5 negative b over 2a. Now, to find the maximum height, you just need to put it in. Plug that value that we just got back into the original equation. We get 140. Now, when does it hit the ground? Okay, well, that's asking for the x-intercepts. I have bad handwriting, but that was ridiculous. Okay, so x-intercepts. So we're going to see, where do we hit the ground? Well, I don't know if it could be factored, but the numbers were pretty complicated. Yeah, that'd be hard to do. Maybe not that bad, actually. But so they just went ahead and did the quadratic. And we're going to get these two times. They did the quadratic, we get these two. Well, if we're talking times, we can't have a negative time. So it's not that one. It must be 5.458 is when it hits the ground. So again, the key to this is that it was an upside down parabola, and the vertex is going to give us the most information. It's going to give us the time and the max height, and then where it hits the ground can be found by being an x-intercept. Okay, so we've only got one more here. Let's try this one. Pause if you want to try it on your own. This is upside down. It's because of the negative, so this is going to allow us to do a maximum problem. Well, when does the rock reach the maximum height? That's looking for the t, which happens to be h. So we're looking for the h of the vertex. I'm just plugging this in to our h formula, negative b over 2a. So I've got negative 96 over negative 32. So, wow, that worked out perfectly. Okay, so that turns out to be 3. So the maximum height is at 3. All right, I mean the time it reaches the maximum height is 3. Now to find the actual maximum height, that's k from our vertex formula, and we find that by just simply putting h back into the formula. Oops. Okay, I'm going to use a calculator. I don't know what these numbers are. Okay, we get 256. So we found h. That tells, plugging it back in finds us k, so we got a maximum height of 256. When do we hit the ground? Well, we're going to try to set this equal to 0. Okay. I'm going to check something real quick here. you can actually pull out negative 16 out of this. I want to see if this can be factored. Okay, so instead of doing the quadratic, I'm pulling out a GCF out of there, which is negative 16. And I believe this can then be factored. No, it can't. I was hoping it could make it a lot easier. So what it can do, well, I'm just going to do it. So we would do the quadratic with negative b plus or minus the square root of b squared. Oh, sorry, I used my other one here. So when does the rock hit the ground? We got our real work cut out for us here. This is going to be negative b is negative 96 plus or minus the square root of b squared minus 4ac all over 2a. Okay, now there's some serious crunching to be done here, and I think, well, I'm definitely using my calculator. I was going to not do it, but let's see what we get. Okay, if I've done this right so far, I've got this. Okay, all of that turns out to be a nice number. So I've got negative 96 plus or minus 128 all over negative 32. All right, so on the top here, we're going to add 128 and subtract it. So I get 32 over negative 32 when I add it. Now that's going to get me negative 1, so I don't want a negative time. But let's do negative 96 minus 128. So if I subtract 128, I get negative 224. I'm going to divide that by negative 32. I get t is 7. So I just did the quadratic with some big ugly numbers, but so I could get rid of the time that's a negative. That's meaningless. But I find that at 7 seconds, 7 seconds is when this rock would hit the ground. That's just the x-intercept. Okay, so because it's a parabola, it's upside down. And so finding the h and the k, find me the time when it reaches the maximum height, and then the actual maximum height is the k. If I want to find when it hit the ground, I'm looking for the intercepts, which you can, here you can do it by the quadratic. And that is the more typical kind. You'll see this projectile being launched or thrown, and you find the vertex or find the x-intercepts to solve it.